record on this computer. Looks like it's recording. Okay, just a couple words on the rest of the week. I'll have office hours scheduled at the normal time on this afternoon. 3:30 is what I've been doing. I'm free tomorrow. I have one business call in the afternoon. I'm free tomorrow and Friday for any office hours you want. I'm available on the weekend. My preference would be that you give me the weekend off. But if you you have a question, we can talk sometime on the weekend. On Sunday, though, you should find that I've posted the final exam. It'll be just a slight, maybe one question or so longer than the midterm was. The focus of that exam is going to be what wasn't on the midterm. The midterm went through chapter 3, the formalism chapter. And of course, we've had no questions on an exam at all on chapter 4, which is hydrogen atom, angular momentum, and spin. Okay, that's 3 great areas right there. And what we've been doing on Monday, and we'll finish up today, which should not take the full hour, on perturbation theory. And that's what's on the schedule. The normal day for our final exam would have been next Tuesday. So of course that'll be the day that the take home is required to be uploaded onto a Canvas. I haven't set a time yet. Usually I do it at the end of the business day. I'll have to look again and see exactly what time our exam would have been had we been doing it in Dunning Hall, and it'll be keyed onto that, I guess. But so the focus is certainly on chapter 4, and then perturbation theory, which is, I guess, chapter 7. But remember, a lot of things we're talking about right now are calculating probabilities. Of course, we talked about that in chapter 1 and some of the examples we did in chapter 2. We specifically showed in chapter 3 why the statistical interpretation associated with probabilities is valid. We did uncertainty problems back in chapter, we did uncertainty back in chapter 2, I guess is one. Now, chapter 1, we introduced the uncertainty principle. Okay, we looked at it again in the formalism, where it became a more generalized uncertainty principle, not just momentum and position and energy and time, but any 2 observables that we said are incompatible. Okay, and it was related to the commutator of those observables. Okay, we had an uncertainty principle there, and I think we even talked about uncertainty with angular momentum in chapter 4, right? And is there an uncertainty principle associated with components of angular momentum or angular momentum squared or whatever? And so things that you'll be putting on the final exam are specifically keyed towards chapter 4 and this perturbation theory stuff. But the chapters 1, 2, and 3 didn't just disappear once we moved into chapter 4. Physics, as you hopefully have noticed by now, as you've been taking more and more physics courses, is a cumulative discipline, and we rest on the shoulders of the earlier chapters every time we take a step forward into a new chapter. Just a couple comments on perturbation theory that we were talking about last time. Any questions on the exam, though, before I move on? It'll be just exactly the same format as the second midterm. Open rules of engagement, exactly the same. Open book, open note. Find a resource somewhere, find a problem somewhere that looks pretty close that you can use as a model. That's fine. You just can't talk to another human being. It has to be your own work. Okay? And you don't have to footnote, but, oh, come on, internet connection. Don't do this to me. Hopefully you're hearing me again. You don't have to footnote your work, but if you are just doing a calculation using Maxima, Mathematica, Wolfram Alpha, what was that other one? MathNet. People use all sorts of different things. So an answer just kind of appears mystically out of nowhere without much written justification. Please give me a hint as to how you got from point A to point B if it was done on some other means. I generally, my solutions work it out, and I know how many lines of algebra or whatever are involved. If that's missing from your paper, I kind of need to know where it came from, and that's general advice for anything that you do in written work moving forward. You're documenting the solution as much as getting an answer. Anyway, on to this perturbation theory. I want to point out that we're doing time-independent perturbation, and furthermore, we're doing a subset of that is non-degenerate perturbation theory. And you'll see why here, as I pointed out in just a second, because this is what we talked about on Monday, just as a brief review. The idea is the Hamiltonian is just what the Hamiltonian would have been in an unperturbed system. And that's the significance of these zeros right here. And then, of course, in an unperturbed system, that would have been the wave function, the eigenfunction, and that would have been the energy eigenvalue for that Hamiltonian. And we superscript it with a zero. Doesn't mean we're raising it to the zero power here. It's just a superscript. And the only reason we're putting it up on the top there is because n is the order. Like for the simple harmonic oscillator, you got energy eigenvalues that are a function of n, actually n squared. And then, we did the hydrogen atom. It's energy eigenvalues are a function of 1 over n squared, that kind of thing. So we've already got n, and the eigenfunction corresponding to every eigenvalue is also subscripted with an n. And so, there are an infinite number of these things for a particular, in principle, for a particular system. We've seen for spin that infinite number collapses in just like 2 choices, right? Up and down, that sort of thing. So n might only be 1 or 2, but n could be up to infinity, as in the case of this simple harmonic oscillator or the infinite square well. In any event, that's the notation that we're using. And so that would have been back in chapter 2. Anything that we learned back in chapter 2, we could have rightfully superscripted with a 0, and that would have been exactly right. The whole point of perturbation theory is if I can take a problem I know, like the infinite square well, right, or the simple harmonic oscillator, or the delta well, or whatever, okay, that has a Hamiltonian with a wave function and an eigenvalue. If I can mathematically define some kind of variation, a perturbation from the perfect system that we've already studied, okay, and that is this thing called H prime here, well, then I can have a new Hamiltonian whose, according to the theory, whose eigenfunctions are psi sub n, where I have a first order correction and a second order correction, on, as many as I really think I need, and eigenvalues with the perfect system with the corrections, okay? In last class, I think we worked up what the first order energy correction was and what the first order corrections, and it's actually plural, are to the wave function. I do want to point out that these lambdas initially were assumed to be small, and that justifies why I'm able to add on more and more terms and eventually stop adding on terms, because lambda gets small and it squares and it cubes, it gets even smaller. We soon just equated like orders of lambda, and then it really didn't matter what lambda was. And so lambda, when you put it all back together, is just unity. Okay, and so it was just a mathematical device so that we can look at all the first order effects, the second order effects if you needed to, the third order effects, etc. And so on Monday, we developed this thing right here, the first order correction to the energy eigenvalue. And it turned out, through some mathematical manipulations, to really just be an expectation value. It is a number, a single correction, okay? If you knew what the parameters were associated with the perturbation, like this guy right here, you know how big it is, you know what the energy height of it is for, in this case, potential energy, you can just find the expectation value of that perturbation. But interesting enough, in the function, in the eigenfunction, in the basis of the unperturbed system, right? The zero system. So in that basis, and presumably you have to know what these are for whatever the unperturbed system would be. And so for us, that kind of limits us to a bunch of things that we've solved: the infinite square well, the finite square well, the simple harmonic oscillator, the delta well. I think those are the only bound systems we've studied in any great detail, other than, of course, then the hydrogen atom, which is a little more complicated, but this theory would work for that as well. Okay, so you presumably have to know these things or be able to look them up in order to figure out what this correction is. All right, and you have to be able to somehow mathematically state what the perturbation is, and that's why it's often things like this. Okay, just a chunk or something with a linear slope. Somehow you can mathematically define that perturbation. That's first order correction. And if you think about it, I think I mentioned this last time, it's probably the most widely used part of perturbation theory, because whenever you do an experiment in a lab, you're going to have some perfect system that we've studied that you're going to be your kind of entry level into what you expect to measure. You'll have this, maybe a simple harmonic oscillator because you got a parabolic potential, and then you've got to come up with a mathematical description of how your system that you've prepared, your subatomic particles, differs from the perfect system. okay? And so you have to be able to mathematically define this H prime. Okay. And if you can do that, you can certainly come up with the correction to the theoretical eigenvalue. And so when you make a measurement and you see it's not the theoretical eigenvalue that you're measuring, but you can come up with a rationale for why it's different, and it happens to be this first order correction, well, you've got something there. You can say this is my potential is slightly different from the theoretical one I was using because I had this perturbation in place, but this perturbation with first order theory completely predicts the difference, and I'm done. I've, experiment equals theoretical prediction, we're done. And oh, by the way, if you want to, then you can go on and figure out what the eigenfunctions would be for your, now that you realize it's your perturbed system, you could go calculate what the eigenfunctions would be, what corrections you would have to make to the perfect eigenfunctions for the unperturbed system. A little bit of problem with that. Here's the equation. You'll notice it's a series, right? It is a series where you have almost it's a Fourier-like series, and it isn't an odd choice that we picked C as the coefficients of these series, because you take all the, if you're looking at the ground state, for example, the n equals 1 state, you add up all the other states, n equals 2, n equals, and it's actually m here, m equals 2, m equals 3, m equals 4, with some amplitude associated with each of those states to correct to the state that is the unperturbed state. And so it's an infinite series. And then the question always becomes, well, how many terms are you going to keep? You'll see on the worksheet, you're told to keep three, the first three terms, which, by the way, doesn't necessarily mean m equals 1, m equals 2, m equals 3, because if there is some reason why a coefficient goes to 0, you see that in Fourier coefficients all the time. A coefficient goes to 0 for maybe all the odd numbers or all the even numbers. You'll see that happening on the worksheet, where one of those, either the odds or the evens, will all go to 0. And so the three lowest terms might be, for example, 1, 3, and 5, or 2, 4, and 6, not 1, 2, 3 like you might want it to be. And I think you'll find exactly what that is. And so, but this piece right here, that bit of mathematics is each of these coefficients. And you notice if you're trying to find corrections, the first order correction to the ground state or the n equals 2 state, you see there for n equals 1 or n equals 2, whatever state you're trying to find the correction to, you've got to do the inner product. Well, you've got to do the expectation value with your perturbed system for all the possibilities where m and n aren't equal to each other. So that's a potentially infinite number of these coefficients, because you would be having an infinite number of eigenfunctions to correct to make the first order correction to the unperturbed eigenfunctions. Okay, and a couple things, I guess, on this. The math gets a little harder in doing this, as opposed to, because the fact that m and n aren't the same as compared to the energy correction, which is a little simpler because these two pieces are the same. All right. This makes the math often a lot harder. And as you look at the title of this slide, it says watch the denominator, because if it turned out that the correction state you're looking for and one of the other states have the same energy eigenvalue, well, we would say that state is degenerate. Okay, those states are degenerate, those two states that have the same eigenvalue. If these two numbers are equal, obviously you're dividing by 0, and this theory falls apart because division by 0 isn't allowed. And that's why we're calling this non-degenerate perturbation theory. When I say watch the denominator, I'm saying that for this particular theory, you cannot have a degeneracy. You can't ever have those two equal to each other. If you do, theory is null and void. There is another theory, another mathematical theory, which you can read on in chapter 7 if you're so inclined. What do you do when you have these two energies being the same for two different states, m and n? Okay, and it's a little bit more complicated. There are these mathematical functions called Wronskians. If you ever heard of these, you put those together. It's kind of cool, but it works. And that's what you have to do to correct the eigenfunctions in that case. All right. So it's a mathematically intensive problem, because remember, this thing in the numerator here is the integral of psi m star times whatever your perturbation is times psi n and then dx integrated over wherever the range of non-zero eigenfunctions is. It could be as much as minus infinity to plus infinity. In an infinite square well like this, it'll be 0 to a, obviously, but that's what it could be. That's a little bit harder, as I said, than doing the case where these two guys are the same. And that's just sort of the way the mathematics works out. Okay, any questions on these first order corrections? So I guess we've so far looked at these two things. We recognize that's just a number or a simple math function. These first order corrections to the wave function, though, to the eigenfunction, it's a series. It could be an infinite series in the most general case, and often we just tell you how many terms to keep, or you figure out, because of the relative size of the terms, how many to keep. Okay, as you might guess, as you get higher and higher in values of m here in this series, C sub m becomes a whole lot smaller, and eventually becomes so small that you just decide it's not worth keeping that additional term. And you'll see exactly that as you start calculating these on the worksheet. You'll see it starts off with like a number greater than one, like, I don't know, I forget the number, 3/2, and then the next one might be 1/4, and then the third one comes down to like 2/32 or some ridiculous number like that. And eventually you see the fourth one would be so small that it's just not worth keeping in the series. Okay, and there's art to how many of these you keep. All right, last chance for questions. I'm going to go on to talk about second order theory then, if nobody has any questions, and we'll talk about, okay, how do you develop that term that you add to the unperturbed energy eigenvalue? We see how to quickly add on a quick correction. How do you get the next correction? And unfortunately, this is going to be a series as well. And so in the correction, you have to determine how many terms to keep. So you have two determinations, really. Do you go on to a third order correction, or how many terms do you keep in the second order correction? Eventually the nonsense has to stop, and you got to go, okay, that's enough. And just we won't be talking about so we're not going to do that, the second order correction to the eigen function. It's complicated enough to get the first order correction with how many terms you're going to keep on that. But you should hopefully be able to see how you would go about getting that from the pattern that we've established with the first and the second order corrections. All right, so on to second order theory. No questions on that? We'll look at it and we'll go, okay, remember it's this blue equation right here, and this came from all the terms that had lambda squared, and I was equating the coefficients of all the terms that had lambda squared in them from expanding out using just regular algebra what the series corrections to both all three, to the Hamiltonian operator, to the energy eigenvalues, and to the wave functions, expand them all out as we did, and these are all the terms that were multiplied by lambda squared. And I've just dropped the lambda squared because I said it's just one. Okay, and as often is the case, the very first thing I'm going to do is pre-multiply every term in the equation by the same thing, and that's the unperturbed wave function for the nth state. Could be the ground state, the n equals 2 state, whatever it is. Okay, and then I put it in our notation here, which tells you to do the integration that I just talked about. So really remember, this is just shorthand for an integral, or perhaps multiplication of matrices. I don't disallow that as a possibility. We've seen that this notation means both, depending on whether you're talking more about the Schrodinger continuous wave function or the more discrete Dirac system. The Dirac system obviously is perfect for describing spins, but for other functions, other potentials, the Schrodinger system of a continuous function is more appropriate. But the fact is, the pattern works either way. In any event, so I said we're going to do this inner product multiplication. And it was interesting that for whatever reason, there were three terms on what I call the energy side of the equation, the eigenvalue side of the equation, that were out there, whereas on the Hamiltonian side, there were only two terms. That's just the way the multiplication and the lumping of terms of equal power of lambda squared worked out, okay? And I guess when I do this integration, I can see, well, these eigenvalues, even the correction eigenvalues, they're just constants. So they come outside the integral, right? That's what I'm doing here, here, and here. And this very last one, you'll notice, it is the inner product of a wave function with itself that is just 1. And so you can see, as before, that's going to be the second order correction right there, times 1 will be equal to everything else as I bring it over to the other side of the equation. And hopefully a couple of these terms will cancel to make my life a little bit easier. Okay. And as before, if you remember, this is exactly the argument we made previously. I'm going to look at this very first term right here, where the unperturbed Hamiltonian is acting on this second order correction to the wave function. Well, I got no idea what that is. Okay, don't know. But I do know that because the unperturbed Hamiltonian is a Hermitian operator, I am perfectly within justification to bring it to the other side. Okay, that is what it means to be Hermitian. And now I do know what that is. That unperturbed Hamiltonian operating on the unperturbed wave function is the unperturbed energy eigenvalue times the unperturbed wave function. And in one step, I brought it outside the integral. I brought that constant outside the integral. And see, I would not have known what the answer is for that, but exploiting the fact that the Hamiltonian is Hermitian allowed me to bring this out here. And then I did know the answer. Okay. And so where I've circled right here, I'm going to plug that in its place. And if you recall, on Monday, this happened once before. Notice that that is the same term that naturally came out right there. It was the unperturbed wave function times the second order correction, unperturbed wave function times the second order correction with the same unperturbed energy eigenvalue right there. So those two terms cancel. Okay. And I think if you recall, and it just worked out, right? The unperturbed wave function and the first order correction wave function here. I think if you go back a slide, you can pretty easily convince yourself that those guys are orthogonal functions. Okay, just look at the way the first order corrections are constructed. We always have two different functions here, and I think they're orthogonal, so that guy just goes away to 0. Okay, and let's see then, what do I have left? If that goes away for us, all I've got is then the second order correction right here has to be equal to that thing right there. Okay, and remember that this first order correction was what we had found on Monday as an infinite series of these coefficients multiplied by the unperturbed wave functions. Okay, and of course we disallow the case where m is equal to n, because that would cause the denominator potentially to go to 0. In fact, not even potentially, would cause the denominator to go to 0. So that isn't part of the sum. It's a mouthful, but I guess at the end of the day, in order to get, now what did I do right here? Yeah, okay. So what I'm doing right here is what I said. I've solved for the second order energy eigenvalue correction, and I'm recalling, and I'm wondering why I wrote this. I'm just recalling from Monday's work what we got for this first order correction. Because remember, these C sub n's we showed on Monday, C sub n's were this thing, was that piece. Okay, well, the second order energy eigenvalue correction contains exactly that series right in there when you're doing this operation. And so it is kind of a mess, I guess. It is kind of a mess because I've got the answer for that. Apparently, these constants, I could bring them out front, right? All these constants right here, I can bring that out front. And then I'm left, because they're just constants inside, brought outside an integral, and I'm left with this thing right here. Okay, if I put the perturbation on the first order corrections, we said that was the first order correction, and so the constants could come out front, and I've got that guy left. And that's, I've talked about that already today, because that is exactly the same thing that's in the numerator of the constant that I brought out front. Okay, and so what that results then is these two things, once you find it, you square it, and you square it in the usual way. You find the magnitude squared, and again, you divide by the two energy values of the correction and then the state that you're trying to find the energy eigenvalue correction to. Okay, and so that it's very similar, oddly enough, to what we found for the first order correction. The difference is in the numerator right here, we square it, and then of course there's no wave function that's multiplied out. But once again, this correction is a series, okay, and you have to make the determination based on the size of these terms in the series, how many of them are worth keeping. And so that's a decision made by how accurate your measurement is in a laboratory and how well you're trying to show correspondence between an unperturbed system and the real system you've constructed in your laboratory. But this term is very handy as well. All right, and so just kind of in recap, I guess. Yeah, let's go back one. I've now figured out for the energy eigenvalues for a non-degenerate system what the first order correction is. Fairly straightforward thing to do, easy to put on a final exam, for example, just give you a perturbation and give you the states and ask what the correction is. A little bit harder to find the first order energy corrections because, as we've just shown, it's now a series of terms, and that's your second order correction. Okay. On the other hand, we've only looked at one correction to the unperturbed wave function. It hopefully wouldn't surprise you that the second order correction would be a second series now of terms constructed in exactly the same way as we constructed the first order series of corrections and the second order series of energy corrections, energy eigenvalue corrections. And you could keep doing this for as many orders as you need to justify the work you're doing in a laboratory. All right. I think that's about all I have to say about perturbation theory, with the one warning again: pay attention to the denominator. If the system you're working with has degeneracies, none of this works. Okay, so this is only keyed to those systems where the energy is non-degenerate, and that worked for infinite square well, simple harmonic oscillator, delta well, finite square well. None of those had degenerate eigenvalues. But as you saw with the energy eigenvalues for, say, the hydrogen atom, there were degeneracies. There were states that were different that would have the same energy, and that becomes a problem with this theory, and so it just doesn't apply. Hey, I think I'm done. About 20 minutes early today because all we had to do was finish up the second order corrections to energy. I think this will be the last time we'll all be together in a group other than the group that comes to office hours. And so I wanted to tell you it's been a pleasure working with all of you this semester. And I hope that, well, first for the seniors, I apologize that for on behalf of the institution, I guess, that you're not going to get an immediate graduation ceremony. You'll have to wait until the fall for that. I think that in no way diminishes your accomplishments. It's just the way things are right now. And for those of you who are, I guess, juniors, I wish you the best as you move on in your physics education, and hope next year is successful. My current plan is I'm not coming back in the fall, but there are some issues with the new hire that was brought in to replace Professor Campbell. He is a foreign national, and if you've been paying attention to the news, you just saw that the president enacted a 60-day hold on work visas for foreign nationals coming into the country. And so that is without a doubt going to affect when Professor Campbell's replacement does arrive on campus. But he has accepted, and he is planning to be here. That 60-day the 60-day thing would only go May 1st, say June 1st, July 1st. He could conceivably still be here in time for the start of the semester. It'll just depend on how fast the processing of the visa comes. He's currently working at CERN. I have one of the reasons why I might not be able to meet with you tomorrow is I'm having a Zoom meeting for him to talk about modern physics, particularly be the course he'll be teaching in the fall, and to pass on to him some of the materials I used and some of the things that we did in the lab in modern physics. But that's I think the future for some of you. I hope you find him an interesting candidate. When I met him, I thought he was a great person, and for you graduates, you won't get to work with the guy, but I think he's going to be a valuable contribution to our physics department. And I wish you all the best of luck next year. All right, that's about it. Any questions? All right, I'll hang around at 3:30 if you haven't started. There's a worksheet due today, which what's the word? Oh, the electric field, and I guess magnetic field interactions with spin. I guess it was just magnetic field, wasn't it? Yeah, magnetic field interactions with spin, the Stern Gerlach stuff, and then the next one due Friday will be the perturbation theory worksheet, which I have to warn you, a little bit mathematical. Use Wolfram Alpha to the maximum extent you can, but I found I ran out of time in the time limit that they give you for free. But that's about all I have to say. Best of luck to everybody. If I don't talk to you again, look for the exam to be posted on Sunday. If you have a particular time where you'd like to meet for office hours, let me know because my schedule's open throughout the weekend. I'll be grading a lot of stuff though. Y'all take care. Have a good day.